Hi guys, welcome back to my channel, and in this video we will be building a softmax classifier from scratch. Scratch means we will only use numpy and no external libraries like PyTorch, TensorFlow, Theano or anything you want. So before getting started, let me show you the results first, and then we will go on into the theory part. So this is my dataset. As you can see, it only consists of x and y's. We are dealing with 2 dimension. 2 features means 2 dimension. It will be much easier to visualize for us being a 3D being. And color is nothing but the labels. So this is the dataset, and this is how my dataset looks like. It has 3 different classes. It's kind of a spiral in shape. I have defined a neural network as well, but let me just show you the results. So this is the result before training, and you can see it is doing a poor job. This is the red region, decision boundary red region, and it is not even classifying properly. So definitely it makes sense because this is prior training, right? And this one is after training, and as you can see, it has done a much better job, quite impressive, I must say, isn't it, for a linear classifier. Now that this is done, we will simply go ahead and I'll just simply clear the outputs and restart this, and we'll jump into the theory. Right, so our neural network looks something like this, where we have our input vector, right? Input vector, this is our x, and this is our output vector, which is s. Output vector is vector, right? We have 2 features, x1 and x2. We'll go on, check the dataset. We have only x and y. This is the x is first feature, y is the second feature, and color is basically the y hat. Sorry, not y hat. Color is basically the y, which means the ground truth, the labels, right? This is a supervised classification. So we have y's. So y being the labels, we have only 3 classes. As you can see over here, we have 3 classes. Means y belongs to discrete set of 3 numbers starting from 0 and ending at 2. So 3 integers. This 0 represents first 1 class, maybe the red class, or 1 represents the blue class, and 2 represents the white class. And you can this network as multilayer perceptron, which is actually the name of this in literature. Multilayer perceptron, why? Because if you see these blue connections, if you remove all the everything from there, if you just see this blue connection, let me just write it down. So this is one perceptron. Then you have another connection. This is another perceptron. Then you have another connection. This is another perceptron. So these 3 make a multilayer perceptron, isn't it? So this is why the name multilayer perceptron is given to these neural networks as well. So the weight matrix, how the weight matrix looks like, it has a weight matrix definitely, and it looks something like this. It has W11, which connects the first node of the input layer to the first node of the output layer. Similarly, you have W12 connects the first node of the input layer to the second node of the output layer. Similarly, W13, W21, and so on and so forth. This weight matrix is of shape 2 by 3, right? Is of shape 2 by 3. So this weight matrix is of shape 2 by 3. Right. Now comes the forward pass. Forward pass is where you calculate this scores. This is the A's vector is for scores. So A's vector is basically W transpose and X. Y transpose? Because X is what? X has dimensions 2 by 1, right? So X has dimensions 2 by 1, means 2 rows, 1 column. It is a vector. Now W has 2 cross 3, and you're trying to multiply that with 2 cross 1. Will this be valid? No, because these 2 are not matching. So you take the transpose of it, and the transpose has a dimension of 3 by 2. Now the number of rows of the X is equal to the number of columns of the weight matrix Now you can multiply them, and the resulting vector will have 3 by 1 dimension, which matches to the 3 by 1 dimension, the score vector. Now after that, what we will do, we will since we are doing softmax classification, we will pass this vector to the softmax function. What this will do, this will create our prediction, like it will create a vector of probabilities, because softmax function is defined as this entity you are seeing over here. And in our case, since we are dealing with only 3 classes, we can write this entire thing as, let's say, this y hat equals nothing but it's e to the power s1, e to the power s2, e to the power s3. This entire thing multiplied by 1 by sum of e to the power si's, and I goes from 1 to 3. Right, so this is our y hat vector. Now before going further, let me just tell you something, that we are only considering a single sample. Single sample has only x, and the ground truth in our case is y. Right, we will only consider single sample to understand this new network better. Now comes the loss function. Loss function is defined as L. It will calculate the loss between y hat, which is the predicted vector, and the y, which is the level, ground truth. It is defined as minus y dot, this is dot product of log of y hat, which is the predicted vector. Now y, as you know, that y is a scalar. Like, how this is possible? Y is scalar. Well, definitely y is a scalar. As you can see over here, y is 1. But we will transform this into something called one hot vector, which is quite hot. Sorry, lame joke. So one hot vector. So one hot vector is basically, let's say you have let's say you have y equals 0. So the corresponding one hot vector will be 1 0 0. Why 1 here? Because if you give indices over here, then one hot vector means that if y is 0 at that position, at that index, give it a 1 is like turning on the bulb over there, and the rest of the bulb, the rest of the LEDs will be 0. Similarly, if this is, let's say, 1, then this is the one hot vector that you get. Similarly, if this is 2, then this will be a one hot vector that you get, where this is turned on, rest of them are turned off. So this is the concept of one hot vector. So this one hot vector, in the next step, we will multiply this with the log of the predicted vector. The predicted vector is nothing but, this is basically y hat. Right, so yeah, let me remove this one. So this entire thing is equals P1, P2 and P3. Right. Now after multiplying, since this is a dot product, after multiplying we will only get minus log of P2. Now P2 is essentially a softmax function, so P2 is basically this element over here divided by this entire thing. So it looks something like this. Right. And using log formulas, if you remember, log a by b is nothing but log of a minus log of b. Applying that logic, we get something like this: minus log of e to the power s2 plus log of this entire thing, which is e to the power s1 plus e to the power s2, and so on and so forth. Right. Now log of e to the power s2 is nothing but s2, because this is the log of with natural logarithm is base e. So this entire thing, this s2 will come out, and the log e base e is basically 1. So hence you get es1, like minus s2, and plus log of this entire thing. Now we'll go to the gradients later, but yeah, before that, if any optimization problem, any neural network problem, if you want to optimize, then you inevitably come to a step where you have to use gradient descent algorithm, which essentially looks something like this: that you have your previous weight, you update that by what? By subtracting some learning rate times del L by del W, isn't it? So this is the reason why we need to calculate this expression del L by del W. And one thing, this is for each and every individual weight. So we have a matrix of weight W, which has 6 weights, right? So for each and everything, we need to for each and every individual weight, we need to calculate the dl by dw's. So that matrix would look something like this. We will call that dw matrix, and that is given by del L by del W11 and del L by del W12, and so on and so forth. Now, why this expression del L by del W? What is the significance of this one? Well, this tells you the rate of change of the loss function with respect to weight. It means that if you tweak W a little bit, means if you change W from W to W plus delta, this is a positive number. This is a non-zero positive number. If you change from W to W plus 1, then what changes can you see in the loss function? Will it increase? Will it decrease? So that sense you can get it from this gradient. So this is my gradient matrix. It is also of shape 2 by 3. Right, now we need to calculate this entire thing. And how are we supposed to do that? Using the magic called chain rule. So this del L by del W11, this entire thing, or in all of these expressions, can be written as chain rule of del L by del S1, because S1 is directly related to the loss function, and S1 by del W11. Now S1 is related to W11 because in here, as you can see, the S vector, which is basically the score vector is something like this. This is essentially W transpose X. So if you compute W transpose X, then this is the vector that you get. And as you can see, W11 is related to S1. Similarly, W21 is also related to S1. Right. So yeah. So in this one, as you can see, del S1 by del W11. Similarly, I have computed it, like I have written down the gradients for every single weight, and it looks something like this. dw, my final dw looks something like this entire big ass matrix. Right, now we need to calculate this expression, like what is dl, like del L by del S1 and del S1 by del dw. But before that, let me tell you that this expression, as you can see, this one is common in this column, right? Next is this expression is also common in this column, and del L by del S3 and del L by del S3 is also common in the third column. Since these all are common in each and every column, we can decompose this entire matrix dlw in this manner, where you have del S by del W11 and del S2 by del W12, and so on and so forth. It has a dimension of 2 by 3, and multiplying that with a diagonal matrix. This is a diagonal matrix with the diagonal elements del L by del S1 and del L by del S2 and del L by del S3. Now if you multiply this, then del L by del S1, this will be multiplied to the first column, and this 0 will be multiplied to the second column, and 0 will be multiplied to the second column as well, and you will get back this entire thing, which is written in pink. Right. So if you compare this, then you will get an idea. Like if you're not familiar with, multiplying a vector with a matrix, like the concept, then you can watch my linear algebra videos. I have explained how you can multiply vectors with matrices an easier way. Or even if you have watched Gilbert Strang's video of matrix multiplication, then this is a piece of cake for you. Anyway, so now the problem boils down to calculating these gradients, right? So let us go ahead and see what del L by del S1 looks like. Let us see. So yeah, in here, so in here I have this expression. This is my loss function, right? Loss y hat by y. This is my loss function. So del L by del S2 will be something like this. If you differentiate this entire thing with respect to S2, then this goes to -1, and the rest thing, log, differentiation of log of something is basically 1 by something, that thing. And then this entire expression, I'm trying to differentiate this entire thing with S2 with respect to S2, and this is a partial derivative, remember, which means anything other than S2 will be treated as a constant. So this is the expression that I will be getting. Right. And this expression, if you see carefully, this is nothing but your P2. Isn't it so? This is nothing but your P2. And this is -1, so ultimately you get P2 -1. Right. P2 -1. Or you can say this is as P of y, P of 1 -1. I'll explain this later while coding. But yeah, let us see del L by del S1. So del L by del S1 is basically this entire expression. You take the entire expression as well and then try to differentiate with respect to del L by del S1. And S2, S1, with respect to S1, S2 is nothing but a constant. This will go to 0. And the rest thing will be nothing but P1. Similarly, del L by del 3 will be P3. Right. So your matrix, your diagonal matrix will look something like this. It has P1 here. This is my P2 -1. And this is my P3. This is my diagonal matrix. Right. This is my 3 by 3 diagonal matrix. Now, I know this one, just computed, and I need to figure out this matrix, right? So del S1 by del W11. Well, this is quite easy, like hell easy. Let me do one thing. Let me just simply, good. Now we will try to calculate what? Del S1 by del W11. So if you look carefully, then with respect to W11, this entire expression is nothing but constant, and we will only differentiate this one, so you will get x1. Similarly, for del S2 and del S2 by del W12, you will get S2 by 12, you will get also x1. So which means you will get a matrix something like this: x1, 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 x2, 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 because of del S1 by del 21, del S1 by del W21. For this one, if we differentiate this entire expression of S1 with W21, this will be treated as constant, and this one, if you differentiate, you will get what? X2. Hence, at this position, you will get X2. Similarly, all the rows will be X2. Now, this is my 2 by 3 matrix, and I can write this in terms of my input vector, which is X vector. Let me write it in different color. So my input vector will be x1, x2. This is 2 cross 1. And if I want to expand that in like this shape, like 2 by 3 shape, I will simply multiply that with a 1 vector, like a vector of 1s. And this is much easier to create in numpy. You just simply use np.1s and you will get this shape, right? And this has a shape equal to 1 times the number of classes, number of classes, right? So this is hashtag class, means the number of classes. Now let's jump into the code, shall we? I hope every mathematics is clear. Now let's jump into the code. So first we will run this cell. We'll import everything. Next is our dataset. Let me run this. This is our lovely dataset. We are taking only 150 points so that it will be much easier to calculate and visualize. Where I have only i5 processor, not that fast. In here, the dataset, I have defined a dataset class, and as you can see, this is basically I'm trying to normalize this. This is the normalization formula, which is basically subtracting the mean and then dividing it by the maximum point minus the minimum point, by the range basically. So this is the min max formula of normalizing. Then while changing the data frame to numpy array, right? So that's clear. And this is I have created a function to plot it, and property is a decorator, and because this will help you, this will allow you to like call functions as an attribute. Right, get item, because if you get item means you can iterate over this data. If you use this get item like special method, then it will help you to iterate over this entire instance of an dataset class. Let us see the data point. Yeah, so this is what my class, like the dataset, looks like. Now here comes the main part. This is my neural network definition. So I have given in features and num class, right? Num class I have stored that into a self.num class. This is my random. I'm taking random weights of shape. This is num class is 2, and in here you can see is 2, and then in features is 2. My input feature is 2 definitely, and num class is 3 because there are 3 classes, right? So this is a matrix of this is a mat of 2 by 3, right? Next, this is the softmax function. So softmax, as you all know, this will first taking the exponent of the input vector, then summing them up and dividing that entire thing by the input vector, right, by this one. So this is the implementation of softmax function. Next is the forward function. Forward function, as you can see, yeah, let me just do one thing. Yeah, it's very cluttered, sorry about that, but yeah, where is it? Forward function. Yeah, forward function, as you can see, this is W transpose and X, W transpose and X, right? W transpose X. Next, we'll pass that through a softmax function, and we'll interpret this as probabilities. As I have said before, that if you pass anything through a softmax function, then the range will be in between 0 and 1, which you can interpret as probabilities. There's no harm in that. Next, I have defined a backward function. Now, backward function in here, if you see this prob is basically like, if you go ahead and see there, this is where it gets interesting. So here, 1, why 1? Because my p vector is what? P1, P2, and P3, right? Index is 1, it's like 0, 1, and 2. So P1 means you select this one, this entire thing. So 1 is also the level of this sample, the data sample that we are dealing with, right? We have already defined that in this sample the ground truth is 1. So in other words, you can write this entire thing, this entire expression. This expression equals to P of y minus 1, right? That is what I have done over here. And I have flattened, ravel means basically it will flatten the array. And this is the diagonal matrix. I've created the diagonal matrix, right? And then after creating the diagonal matrix, I am doing one multiplying. First, I am multiplying self.x with num np1s, right? This is basically the implementation of, well, let me show you. This is basically the implementation of, yeah, this one. The line number 20 is the implementation of this one, right? np1s will give you an array like this, and then you will multiply that with the x, you will get a matrix of 2 by 3. Okay. Now the next step is you multiply this entire matrix, which is nothing but, this matrix is nothing but your first matrix, this one. Then you multiply this with the diagonal matrix. So this is your diag. Let me just erase everything. Yeah, it's getting clearer. So this is your diagonal matrix and this is your dw, right? And this entire thing will be your ultimate dw, which you will be using to update the weights. So let's run this cell. Done. Next is this one. So this one, let me just go through it. So I have created the model, like them called the model. Then TQDM is basically for to get an idea like how long will it take. And this is a mesh grid. Mesh grid, if you don't know, then what this does is it returns two arrays, and this x1 and y1 is basically the transpose of each other. And this is very useful to creating contours. You know that the contour, we have given this contour function. I'll show you what contour means, basically what contour looks like. So contours is basically, it will help you to create the decision boundary, right? So I'm taking the y and reshaping this into 2 cross 1 the column vector, then passing that to the forward function, getting the dw's, which like backward function will basically calculate the gradients, and then updating the weights with learning rate 0.001. This is my learning rate, right? So this is the gradient updation step. And if I run this cell, this is what it looks like. And if I run this one, this will train the model, and you can spot the difference clearly. I have used 2000 epochs. I hope that will be enough. And contour to plot this sort of decision boundaries, you know. There you have it. It's quite beautiful, isn't it? Like, let me just split the screen. So this is my ultimate output and this is the previous output, right? Like, now that is something interesting, isn't it? Now you can do one thing. You can animate this entire thing. So for example, I need to wrap this entire function into this thing and then train, right? I hope this would do. So let me run this. Let me just restart. Let me just interrupt. Right, restart everything, run all. Yeah, okay, finally. Let me play it. Oh yeah, there you have it. Now that is something which is interesting and beautiful, isn't it? Alright then, I hope you enjoyed the video. Let me know your thoughts in the comment section below, and yeah, see you next time. Adios. Thanks for watching.